Hello and welcome to our video presentation on the Data Analytics Challenge for the Formula AI Hackathon. These are our pillars. Our product Twin AI is a unique blend of two powerful machine learning models, one for predicting weather type at a specific time in future and the other for predicting the probability of rainfall. The problem we aim to solve is improve overall performance in the game, which is hampered by unexpected weather conditions and inaccurate weather predictions. Our solution improves game quality by building machine learning models which can successfully predict the time, duration, and changing weather conditions with excellent precision. We also have developed a Twin AI web app which can test other types of weather-based data with the features observed by the model to successfully generate an output. Our prototype design began with a strategy that connected the dots from user experience research to deployment. Our workflow was also taken through various steps, including the initial data analysis, modeling, and deployment.
For the Formula One hack, we leverage the Oracle storage to deploy our services, one of which is the Oracle bucket. We also leverage the container registry to deploy our Docker image, which was used to serve the solution via Kubernetes.
Now here's a quick walkthrough of our machine learning workflow. First of all, we set up a Jupyter Notebook instance using the Oracle Data Science Cloud service. We used Oracle Cloud GPU kernels to build our experiments for fast iterations. For the purpose of the challenge, we carried out a comprehensive analysis of the data. We split up our workflow into 4 individual sections. During the initial data analysis and pre-processing phase, we checked for label ambiguity, treated every data integrity issues that we noticed from the data. This allowed us to obtain a very suitable and consistent data set that we now utilize for further exploratory data analysis. We began this phase with a very comprehensive multivariate analysis to understand the distribution of the data, to make the right assumptions about the data, and to have very strong insights by which we're going to treat the selection of our features. We use heat maps to explore correlations in the data. We also noticed sub-components of strongly correlated portions of the data, but weakly correlated to our target outcomes. Now we began to explore the distributions in the data. Particularly, we're interested in features that could give the best variations with respect to time and with respect to the target outcomes. Now we ran 2 phases of feature selection experiments. We first performed a generic univariate select using Kepler variable importance. Then we implemented recursive feature elimination. We built a summary table that showed us features that were accepted by both algorithms, and our aim was to pick out those individual features that were accepted by both, and for the rest of the features that were accepted by one but eliminated by the other, we used some sort of intuition based on current understanding of the game and of the data to make reasonable judgment about which features to select and continue working with. At the end of this phase, we ended up with 10 features totally, 8 input features, and then the weather outcome and the percentage outcome. For the machine learning phase of the project, we ran a couple of experiments with classification and regression. Our approach was not to build a single model or a multi-output model. We wanted to be more precise by building a classifier for the weather conditions to classify weather type, and then building a regressor that gives us the predicted rain percentage. Then we combine the 2 models to work together in order to give us predictions for any input data. For each model we built, we ran variations with standardization and without standardization. For the model experiments with classification, we experimented with 4 classifiers. At the end of our experimentations using standardization and without standardization, we created a leaderboard of challenger models, and we observed that the XGBoost classifier performed the highest across all variations. For our regression experiments, we built 4 models: random forest regressor, light GBM regressor, elastic net regularized regression with grid search optimization, and the XGBoost regression. We noticed again that the XGBoost regression outperformed the other models. Typically, our evaluation metrics that we use for these models were the log loss, which is the cross entropy loss that allows us to assess the inaccuracy of categorization, and then for regression we used mean absolute error. Now for the summary table for our champion models, we see very impressive scores. Our log loss was 0.000018 and our mean absolute error was as low as 2.072. So in the course of this workflow, we've been able to achieve very high performing models that made very accurate predictions on our test data. And so we decided to take these models into production, deploying the models into a containerized service on Kubernetes via Oracle Cloud. And then we've also built an application that consumes the model API via UI.
The business value of Twin AI has a social impact that improves user experience and game immersion. It provides enormous business value that can scale a product's success over time. These are the major team players behind the build and success of Twin AI. Thank you for watching.